A radio direction finder is a device for finding the direction, or bearing, to a radio source. The act of measuring the direction is known as radio direction finding or sometimes simply direction finding. Using two or more measurements from different locations, the location of an unknown transmitter can be determined. Alternately, using two or more measurements of known transmitters, the location of a vehicle can be determined. RDF is widely used as a radio navigation system, especially with boats and aircraft. RDF systems can be used with any radio source, although the size of the receiver antennas are a function of the wavelength of the signal. Very long wavelengths require very large antennas, and are generally used only on ground-based systems. These wavelengths are nevertheless very useful for marine navigation as they can travel very long distances and over the horizon, which is valuable for ships when the line of sight may be only a few tens of kilometers. For aerial use, where the horizon may extend to hundreds of kilometers, higher frequencies can be used, allowing the use of much smaller antennas. An automatic direction finder, often tuned to commercial AM radio broadcasters, is a feature of almost all modern aircraft. For the military, RDF systems are a key component of signals intelligence systems and methodologies. The ability to locate the position of an enemy broadcaster has been invaluable since World War I, and play a key role in World War II's Battle of the Atlantic. It is estimated that the UK's advanced half-DUF systems were directly or indirectly responsible for 24% of all U-boats sunk during the war. Modern systems often used phased array antennas to allow rapid beamforming for highly accurate results. These are generally integrated into a wider electronic warfare suite. Several distinct generations of RDF systems have been used over time, following the development of new electronics. Early systems used mechanically rotated antennas that compared signal strengths in different directions, and several electronic versions of the same concept followed. Modern systems use the comparison of phase or Doppler techniques which are generally simpler to automate. Modern pseudo-Doppler direction finder systems consist of a number of small antennas fixed to a circular card, with all of the processing occurring in software. Early British radar sets were also referred to as RDF, which was a deception tactic. However, the terminology was not inaccurate. The Chain Holmes systems used separate omnidirectional broadcasters and large RDF receivers to determine the location of the targets. History Early mechanical systems The earliest experiments in RDF were carried out in 1888 when Heinrich Hertz discovered the directionality of an open loop of wire used as an antenna. When the antenna was aligned so it pointed at the signal it produced maximum gain, and produced zero signal when face-on. This meant there was always an ambiguity in the location of the signal, it would produce the same outputs if the signal was in front or back of the antenna. Later experimenters also used dipole antennas, which worked in the opposite sense, reaching maximum gain at right angles and zero when aligned. RDF systems using mechanically swung loop or dipole antennas were common by the turn of the 20th century. Prominent examples were patented by John Stone in 1902 and Lee de Forest in 1904, among many other examples. By the early 1900s, many experimenters were looking for ways to use this concept for locating the position of a transmitter. Early radio systems generally used medium-wave and long-wave signals. Long-wave in particular had good long-distance transmission characteristics due to their limited interaction with the ground, and thereby provided excellent great circle route ground wave propagation that pointed directly to the transmitter. Methods of performing RDF on long-wave signals was a major area of research during the 1900s and 1910s. Antennas are generally sensitive to signals only when they have a length that is a significant portion of the wavelength, or larger. Most antennas are at least a 1/4 of the wavelength, more commonly a 1/2. The half-wave dipole is a very common design. For long-wave use, this resulted in loop antennas tens of feet on a side, often with more than one loop connected together to improve the signal. Another solution to this problem was developed by the Marconi Company in 1905. This consisted of a number of horizontal wires or rods arranged to point outward from a common center point. A movable switch could connect opposite pairs of these wires to form a dipole, and by rotating the switch the operator could hunt for the strongest signal. The U.S. Navy overcame this problem, to a point, by mounting antennas on ships and sailing in circles. Such systems were unwieldy and impractical for many uses. Bellini to C equals. A key improvement in the RDF concept was introduced by et al. Bellini and Alessandro Tossi in 1909. Their system used two such antennas, typically triangular loops, arranged at right angles. The signals from the antennas were sent into coils wrapped around a wooden frame about the size of a pop can, where the signals were recreated in the area between the coils. A separate loop antenna located in this area could then be used to hunt for the direction, without moving the main antennas. This made RDF so much more practical that it was soon being used for navigation on a wide scale, often as the first form of aerial navigation available, with ground stations homing in on the aircraft's radio set. Bellini to C direction finders were widespread from the 1920s into the 1950s. Early RDF systems were useful largely for long-wave signals. These signals are able to travel very long distances, which made them useful for long-range navigation. However, when the same technique was being applied to higher frequencies, unexpected difficulties arose due to the reflection of high-frequency signals from the ionosphere. The RDF station might now receive the same signal from two or more locations, especially during the day, which caused serious problems trying to determine the location. This led to the 1919 introduction of the Adcock antenna, which consisted of 4 separate monopole antennas instead of 2 loops, eliminating the horizontal components and thus filtering out the sky waves being reflected down from the ionosphere. Adcock antennas were widely used with Bellini to C detectors from the 1920s on. The U.S. Army Air Corps in 1931 tested a primitive radio compass that used commercial stations as the beacon. Half duff equals. A major improvement in the RDF technique was introduced by Robert Watson Watt as part of his experiments to locate lightning strikes as a method to indicate the direction of thunderstorms to sailors and airmen. He had long worked with conventional RDF systems, but these were difficult to use with the fleeting signals from the lightning. He had early on suggested the use of an oscilloscope to display these near instantly, but was unable to find one while working at the Met Office. When the office was moved, his new location at a radio research station provided him with both an Adcock antenna and a suitable oscilloscope, and he presented his new system in 1926. In spite of the system being presented publicly, and its measurements widely reported in the UK, its impact on the art of RDF seems to be strangely subdued. Development was limited until the mid-1930s, when the various British forces began widespread development and deployment of these high-frequency direction finding, or half-duff systems. To avoid RDF, the Germans had developed a method of broadcasting short messages under 30 seconds, less than the 60 seconds that a trained Bellini to C operator would need to determine the direction. However, this was useless against half-duff systems, which located the signal with reasonable accuracy in seconds. The Germans did not become aware of this problem until the middle of the war, and did not take any serious steps to address it until 1944. By that time half-duff had helped in about 1/4 of all successful attacks on the U-boat fleet. Post-war systems several developments in electronics during and after the war led to greatly improved methods of comparing the phase of signals. In addition, the phase lock loop allowed for easy tuning in of signals, which wouldn't drift. Improved vacuum tubes and the introduction of the transistor allowed much higher frequencies to be used economically, which led to widespread use of VHF and UHF signals. All of these changes led to new methods of RDF, and much more widespread use. In particular, the ability to compare the phase of signals led to phase comparison RDF, which is perhaps the most widely used technique today. In this system the loop antenna is replaced with a single square-shaped ferrite core, with loops wound around 2 perpendicular sides. Signals from the loops are sent into a phase comparison circuit, whose output phase directly indicates the direction of the signal. By sending this to any manner of display, and locking the signal using PLL, the direction to the broadcaster can be continuously displayed. Operation consists solely of tuning in the station, and is so automatic that these systems are normally referred to as automatic direction finder. Other systems have been developed where more accuracy is required. Pseudo-Doppler radio direction finder systems use a series of small dipole antennas arranged in a ring and use electronic switching to rapidly select pairs of dipoles to feed into the receiver. The resulting signal is processed and produces an audio tone, whose frequency is dependent on the direction of the signal. Doppler RDF systems have widely replaced the half-duff system for location of fleeting signals, as it does not require an oscilloscope. Operation. Radio direction finding works by comparing the signal strength of a directional antenna pointing in different directions. At first, this system was used by land and marine-based radio operators, using a simple rotatable loop antenna linked to a degree indicator. This system was later adopted for both ships and aircraft, and was widely used in the 1930s and 1940s. On pre-World War II aircraft, RDF antennas are easy to identify as the circular loops mounted above or below the fuselage. Later loop antenna designs were enclosed in an aerodynamic, teardrop-shaped fairing. In ships and small boats, RDF receivers first employed large metal loop antennas, similar to aircraft, but usually mounted atop a portable battery-powered receiver. In use, the RDF operator would first tune the receiver to the correct frequency, then manually turn the loop either listening or watching an S-meter to determine the direction of the null of a long-wave or medium-wave broadcast beacon or station. This null was symmetrical, and thus identified both the correct degree heading marked on the radio's compass rose as well as its 180-degree opposite. While this information provided a baseline from the station to the ship or aircraft, the navigator still needed to know beforehand if he was to the east or west of the station in order to avoid plotting a course 180 degrees in the wrong direction. By taking bearings to two or more broadcast stations and plotting the intersecting bearings, the navigator could locate the relative position of his ship or aircraft. Later, RDF sets were equipped with rotatable ferrite loopstick antennas, which made the sets more portable and less bulky. Some were later partially automated by means of a motorized antenna. A key breakthrough was the introduction of a secondary vertical whip or sense antenna that substantiated the correct bearing and allowed the navigator to avoid plotting a bearing 180 degrees opposite the actual heading. The U.S. Navy RDF model SE 995, which used a sense antenna, was in use during World War I. After World War II, there were many small and large firms making direction-finding equipment for mariners, including Apelco, Aquaguide, Bendix, Gladding, Ray Jefferson, Raytheon, and Sperry. By the 1960s, many of these radios were actually made by Japanese electronics manufacturers, such as Panasonic, Fujionko, and Koden Electronics Company, Limited. In aircraft equipment, Bendix and Sperry Rand were two of the larger manufacturers of RDF radios and navigation instruments. Usage in maritime and aircraft navigation. Radio transmitters for air and sea navigation are known as beacons and are the radio equivalent to a lighthouse. The transmitter sends a Morse code transmission on a long-wave or medium-wave frequency incorporating the station's identifier that is used to confirm the station and its operational status. Since these radio signals are broadcast in all directions during the day, the signal itself does not include direction information, and these beacons are therefore referred to as non-directional beacons, or NDBs. As the commercial medium-wave broadcast band lies within the frequency capability of most RDF units, these stations and their transmitters can also be used for navigational fixes. While these commercial radio stations can be useful due to their high power and location near major cities, there may be several miles between the location of the station and its transmitter, which can reduce the accuracy of the fix when approaching the broadcast city. A second factor is that some AM radio stations are omnidirectional during the day, and switch to a reduced power, directional signal at night. RDF was once the primary form of aircraft and marine navigation. Strings of beacons formed airways from airport to airport, While marine NDBs and commercial AM broadcast stations provided navigational assistance to small watercraft approaching a landfall. In the United States, commercial AM radio stations were required to broadcast their station identifier once per hour for use by pilots and mariners as an aid to navigation. In the 1950s, aviation NDBs were augmented by the VOA system, in which the direction to the beacon can be extracted from the signal itself, hence the distinction with non-directional beacons. Use of marine NDBs was largely supplanted in North America by the development of LORAN in the 1970s. Today many NDBs have been decommissioned in favor of faster and far more accurate GPS navigational systems. However, the low cost of ADF and ADF systems, and the continued existence of AM broadcast stations has allowed these devices to continue to function, primarily for use in small boats, as an adjunct or backup to GPS. Automatic Direction Finder. An automatic direction finder is a marine or aircraft radio navigation instrument that automatically and continuously displays the relative bearing from the ship or aircraft to a suitable radio station. ADF receivers are normally tuned to aviation or marine NDBs operating in the LW band between 190–535 kHz. Like ADF units, most ADF receivers can also receive medium-wave broadcast stations, though as mentioned, these are less reliable for navigational purposes. The operator tunes the ADF receiver to the correct frequency and verifies the identity of the beacon by listening to the Morse code signal transmitted by the NDB. On marine ADF receivers, the motorized ferrite bar antenna atop the unit would rotate and lock when reaching the null of the desired station. A center line on the antenna unit moving atop a compass rose indicated in degrees the bearing of the station. On aviation ADFs, the unit automatically moves a compass-like pointer to show the direction of the beacon. The pilot may use this pointer to home directly towards the beacon, or may also use the magnetic compass and calculate the direction from the beacon at which their aircraft is located. Unlike the RDF, the ADF operates without direct intervention, and continuously displays the direction of the tuned beacon. Initially, all ADF receivers, both marine and aircraft versions, contained a rotating loop or ferrite loopstick aerial driven by a motor which was controlled by the receiver. Like the RDF, a sense antenna verified the correct direction from its 180-degree opposite. More modern aviation ADFs contain a small array of fixed aerials and use electronic sensors to deduce the direction using the strength and phase of the signals from each aerial. The electronic sensors listen for the trough that occurs when the antenna is at right angles to the signal, and provide the heading to the station using a direction indicator. In flight, the ADF's RMI or direction indicator will always point to the broadcast station regardless of aircraft heading. However, a banked attitude can have a slight effect on the reading. The needle will still generally indicate towards the beacon, however it suffers from dip error where the needle dips down in the direction of the turn. This is the result of the loop itself banking with the aircraft and therefore being at a different angle to the beacon. For ease of visualization, it can be useful to consider a 90-degree bank turn, with the wings vertical. The bearing of the beacon as seen from the ADF aerial will now be unrelated to the direction of the aircraft to the beacon. Dip error causes the needle to point more towards the wing in a turn. It is sometimes wrongly confused with quadrantal error, which is the result of radio waves being bounced and re-radiated by the airframe. Quadrantal error does not affect signals from straight ahead or behind, nor on the wingtips. The further from these cardinal points and the closer to the quadrantal points the greater the effect, but quadrantal error is normally much less than dip error, which is always present when the aircraft is banked. ADF receivers can be used to determine current position, track inbound and outbound flight path, and intercept a desired bearing. These procedures are also used to execute holding patterns and non-precision instrument approaches. Typical NDB services ranges station passage as an aircraft nears an NDB station, the ADF becomes increasingly sensitive. Small lateral deviations result in large deflections of the needle which sometimes shows erratic left-right oscillations. Ideally, As the aircraft overflies the beacon, the needle swings rapidly from directly ahead to directly behind. This indicates station passage and provides an accurate position fix for the navigator. Less accurate station passage, passing slightly to one side or another, is shown by slower swinging of the needle. The time interval from the first indications of station proximity to positive station passage varies with altitude a few moments at low levels to several minutes at high altitude. Homing equals, the ADF may be used to home in on a station. Homing is flying the aircraft on the heading required to keep the needle pointing directly to the 0° position. To home into a station, tune the station, identify the Morse code signal, then turn the aircraft to bring the ADF azimuth needle to the 0° position. Turn to keep the ADF heading indicator pointing directly ahead. Homing is regarded as poor piloting technique because the aircraft may be blown significantly or dangerously off course by a crosswind, and will have to fly further and for longer than the direct track. Tracking equals, the ADF may also be used to track a desired course using an ADF and allowing for winds aloft, winds which may blow the aircraft off course. Good pilotage technique has the pilot calculate a correction angle that exactly balances the expected crosswind. As the flight progresses, the pilot monitors the direction to or from the NDB using the ADF, adjusts the correction as required. A direct track will yield the shortest distance and time to the ADF location. Radiomagnetic indicator equals. A radiomagnetic indicator is an alternate ADF display providing more information than a standard ADF. While the ADF shows relative angle of the transmitter with respect to the aircraft, an RMI display incorporates a compass card, actuated by the aircraft's compass system, and permits the operator to read the magnetic bearing to or from the transmitting station, without resorting to arithmetic. Most RMIs incorporate two-direction needles. Often one needle is connected to an ADF and the other is connected to a VOR. Using multiple indicators, a navigator can accurately fix the position of their aircraft using triangulation, without requiring the aircraft to pass over the top of the station. Some models allow the operator to select which needle is connected to each navigation radio. There is great variation between models, and the operator must take care that their selection displays information from the appropriate ADF and VOR. This instrument display can replace a magnetic compass display in the instrument panel, but not the gyroscopic heading indicator. The heading indicator can be combined with information from navigation radios in a similar way, to create the horizontal situation indicator. The HSI, along with the VOR system, has largely replaced use of the RMI, however the HSI's much higher cost keeps the older combination of an RMI and an OBI attractive to cost-conscious pilots. See also, acronyms and abbreviations in avionics, amateur radio direction finding, cardioid, battle of the beams, radio navigation, VOR DME, radio direction finding, traffic analysis, HFDF, Woolen-Weber, real-time locating. Notes. References, Boffa PD, Sistemi per la radionavigation, ed. Sideria, 1985, V. Piazzi, Sistemi radioeltrici di navigazione, Vol V, AA, Artrebi, Strumenti e navigazione, ed. Aviabooks of France Scotti, Avionica, ed. Avialibri, Alessandro Tisci, e radiogonia Metro Bellini Tisci alla esposizione di storia della scienza in Firenze, Taranto, A. Dragonum C., 1929, Alessandro Tisci, L'Enciclopedia Italiana e Radiosistema Radiogonio Metro, Pisa, Pacini Moiotti, 1932, Alessandro Tisci, Contributo della Marina all'Evento del Radiogonio Metro, Roma, E. Pinci, 1929, Apparati Arti di Bordo e Radiogonio Metro, Ministero dell'Aeronautica Ispettorato Scuole, Roma, 1937, Impiego Pratico del Radiogonio Metro d. FM 3 Sonavi Mercantili, Ministero del Post e del Telecomunicazioni, Roma, Ist. Poligr. Dello Stato, 1950, Musella, Francesco, Il radiogonio metro ed il radio faro nella navigazione, Roma, Est. Poligr. Dello Stato, 1934, Radiogonio metro Marconi per uso di bordo, typo 11F, Roma, Tip. Radio, 1926, Catalogo illustrato per Radiogonio metro P57N Campale, Siemens S.A., Ministero della Guerra, Divisione Superiore del Servizio Studi ed Esperimenti del Genio, Milano, Tip. El Tofalini, 1942, Istruzioni per l'uso dell'alimentatore TF109 per Radiogonio metro e risvettore, a cura della Siemens, Ministero dell'Aeronautica, Ufficio Centrale del Telecomunicazioni e dell'Assistenza del Volo, Milano, 1941, Catalogo illustrato per impianto Radiogonio metro E393N, Siemens SN, Ministero della Guerra. Divisione Superiore del Servizio Studi ed Esperimenti del Genio, Milano, Tip. El Tofalini, 1942, 21, Il Radiogonio metro Marconi per stazioni terrestri, typo 12A, Roma, Ufficio Marconi, 1923, Tisci, A. Il Radiosistema Bellini Tisci Radiogonio metro, l'ultima face, Taranto, Artigraphiche Dragone, 1930, 23, Radiogonio metro Marconi per Aeromobili, typo 14, Codice Roma, Ufficio Marconi, e Genova, Officine Radiotelegrafiche Marconi, 1923, Il Radiogonio metro e la Radiotelegrafia Diativa, Ufficio Marconi, Roma, Tip. Union ed. 1920, Radiogonio metro Marconi per uso di bordo, descrizione, funzionamento, manutenzione, impiego nella condotta della navigazione, Genova, Tip. Radio, 1923, Radiogonio metro Marconi R, GM3. Istruzioni per l'uso e la manutenzione del segnale d'allarme automatico senza regolaggio typo S. FR, Roma, Est. Professor G. Marconi, 1950, Radiogonio metro Marconi R, GM3. Istruzioni per l'uso e la manutenzione del segnale d'allarme automatico senza regolaggio typo S. FR, Roma, Est. Professional di Radiotelegrafia G. Marconi, 1949, Radiogonio metro indicatore di rotta typo P63N, descrizione ed istruzioni per l'uso, Ministero dell'Aeronautica, Divisione Generale del Costruzioni e degli Approvvigionamenti, Milano, Tofalini, 1941, Impiego pratico del Radiogonio metro DFM. 3 Salnavi Mercantili, Ministero delle Comunicazioni, Divisione Generale del Post e dei Telegrafi, Roma, Est. Poligr. Stato, 1932, Vincenzo Nastro, Gabriele Messina, Navigazione radiogoniometrica, in Navigazione Area, Milano, Hoepli, 2002, pages 213 a Euro 262. ISBN 88-203-2942-5. External links, Flash-based radiomagnetic indicator simulator.